handout, which I'll be posting on Blackboard as well. The handout's called Abandoning Richter. I told you I was going to hand it out today. And that's about why we don't use the Richter scale anymore. So that when you go for an interview somewhere, you don't embarrass yourself. You say that I got a good pedigree going to Missouri S&T, and they told me what's actually going on. But the reason is the stuff that I showed you last week. It's about site response, magnifying the body waves, and so they're not reliable. Surface measurements aren't reliable indication. I hope I don't run out. I may run out here. 1, 2, 3. Yeah, I'm going to run out. Looks like you guys already? Mm-hmm. 1, 2. Oh, 1, 2. Looks like I'm too short. Okay. I'll see if I have some more. Hang on. Anyway, this is a nice, concise write-up. It's only 4 pages, not even 4, actually. And that's the best thing I've seen out there in terms of not chewing up more paper than it's worth to explain to you what's going on. So that'll be covered on the final, the stuff that's in this little handout I'm giving you. I have the final scheduled for next Monday, a week from today, the same time slot, 4 to 6. Is that what you all have too? Okay. All right. It's a multiple choice open book final. That's not, I'm not going to try to make it hard for you. And usually, if you've done all the work and everybody scores pretty well on it. The distance learners always score 10 points higher on average than the class learners because my classes tend to be much more practice-oriented because I spent 25 years in practice before I got here. So I don't tend to ask theory questions. I tend to ask more about things that I covered in the lectures, which are more concept-type things. But it's multiple choice, and it shouldn't stump any of you if you've just done the basic work and you show up. And if you ask a question, I will answer that question for everybody. So it doesn't matter what. If you think something is really not clear, come up and ask me. That's what I want you to do when you go to work somewhere. Come up and ask the boss and say, "Boss, I just don't quite get this." And I understand that. I had 5 children. And my wife and I miscommunicate every day of the week for 30 years. So there's always going to be communication things that are different because the way we communicate is predicated on our own unique pedigree of experience with how we're raised, what culture we're raised in, and that kind of thing. So I understand that. I'm going to take the sweater off because I'm already too hot. Just a second. All right. Now, questions. David, you had some questions you wanted to cover.
I just noticed some errors on the homework, but
okay.
One of them was, I think the first problem, the answer should be 118 west, and it's given as 18 degrees west.
All right. Right, so there's a typo.
Yeah, there's
probably.
a typo, but
all right.
the only question I had, I think I did the statics part wrong. On the very last problem, you had some parallel pipettes that were 1 meter by 1 meter base and then different heights. And how did you, I was trying to figure out how you determined why the last few toppled over and the ones right below it didn't.
Because you have a higher center.
Yeah, we're using the centroid and then you use the force
right
at the centroid, but did you compare that to the friction force?
Yeah, you have to look at the friction force. And we usually assume a friction of 0.3 on the base, rock to rock.
They gave it as 0.2.
0.2. Yeah, that means it's polished.
Yeah.
So, but that was like that case I told you last week about the water cistern that had a concrete top on it that weighed over a ton, and it was completely thrown off. So we went back and used a 0.35, 0.3, 0.25, and in all of those we had to get more than a G lateral force to knock that thing off. So When you get up on top of ridge lines, that's where you really get a topographic effect. If it's a steep enough ridge line, if it's a flat ridge, you're not going to get it. But a steep enough ridge, that it's called the flagpole effect. It's really going to whip around up there because it's unconstrained. And so that's where the connection details in the structure are so important. I mean, that Loma Prieta earthquake, these houses looked like they had been blown up in an aerial attack. There was just splinters everywhere. And then all of a sudden, there was an A-frame house perfectly right between all the destroyed ones. Right, same geology, and you're going, wow, what's different here? Well, we went down to the county records after they opened up 6 weeks later, got into the building files for those buildings, and that building that was the A-frame had been built for a doctor. The doctor had hired a mainstream architect. The architect had subbed out some work to a mainstream structural engineer. The mainstream structural engineer specified diaphragm framing system, and A-frames at diaphragms. That's all kinds of shear wall. So your shear wall and your diaphragm, the same thing, it's the roof, and connection details. So it performed very, very well. The other ones were owner-builders, which we have lots of in this state, where, don't tell me how to build anything, don't want your building code infringing on my freedom. And they went out and built their own places, which cost more money than the one that came through, actually, without any damage. But it's when you go on those kinds of field trips and see those kinds of things that you realize the connection details are everything. Yeah.
Speaking of that, I watched a show on, I think it was Discovery, on Haiti, and it was, besides the fact that they didn't have steel reinforced concrete, it said if they had had the right connections between the floors, it wouldn't have come down the way it did. It would have at least been fail-safe, and they said it wouldn't have cost more than about 15% more. And you said
that's
more
a
like
high number. That's a real
you said
high
more
number.
like 2 or something.
Yeah, it shouldn't be more than 2%. 0.5% is typical on a new construction. 2% when you're trying to retrofit something. So, when they're higher numbers, sometimes if they do concrete, like when we were at the Kobe earthquake, one of the things that I saw was they came out with all of their steel, and all the steel were the same lengths. They were about 12 foot long, 4 meters. And then they lapped all of them at exactly the same spots. So they had nice laps. They were overlapping about 21 inches. But you have that soft transition at exactly the same height throughout the structure. So when the earthquake came along, and of course with each cycle of loading, the building cracks some. And that degrades the natural fundamental period of the structure. Well, these buildings all broke right along the lines where all the laps were. They didn't stagger the laps. You look in the Los Angeles code, way back in '67, they started putting in there, you have to stagger the laps. You can't make all the laps at 12 feet. Then you're going to have a built-in weakness zone throughout the structure. But those are the kind of things, you learn when you go out to earthquakes and you see how things fail. If you ever get a chance to go out on any kind of disaster, go. Just go. Because you're going to learn things that are very hard to learn in the classroom. You're going to see things that are hard to see, that are emotionally trying, especially on Haiti. But you remember, our codes aren't meant to protect the structure. They're life safety. So that means you have to tear the building down and you have to put a new building up after the earthquake. If you want the earthquake to be safer than that, like we do for a lot of security installations, military installations, fire stations, police stations, hospitals, then they have to be designed to a higher standard, engineering-wise. And that's called a functionality criteria. That's so you want it to function after your disaster and during the recovery phase of the disaster. Then you have to spend more money. But you got to realize this really came up in a big way after Hurricane Katrina. I was on the National Science Foundation funded team that was looking at the flood control infrastructure, and we were looking at the offshore infrastructure, the offshore platforms. And way back in 1973, Shell Oil had looked at their offshore platforms in the wake of a platform leak in the Santa Barbara Channel in 1969, which had cost the oil industry dearly because there's a lot of wealthy people that live in Santa Barbara. There's more Fortune 500 CEOs that live there than any other city in America. And when this oil started washing up on the beach, those people just said, no more oil drilling in our backyard. It's okay in your backyard and yours, but not in our backyard. No more oil drilling. So the oil industry took that and said, what can we do to make these things safer so we don't have something like what happened in Santa Barbara? And this is, almost 40 years ago. And so they started looking at all the different things, and they started looking at these new categories of hurricanes. And they said, what if we have a repeat of a Category 5? Well, they'd only seen a Category 5 in 1900, the Galveston earthquake. So that was 73 years previous. And when they started looking at cost-benefit ratio, they found that once you get the factor safety, typically you design for 1.5, and the Corps of Engineers had decided back in the early 30s to design levees for 1.3. Well, that was because back in those days, those levees were pretty much to protect agricultural areas, not high-density urban areas. So you use a lower factor of safety because all you're going to lose is a year's worth of cotton crops if that levee breaks. But if you apply that 1.3 factor of safety to a densely populated urban area, you're putting that area at considerable risk because 30% isn't much when you look at all the unknowns. So you look at Shell Oil, what did they do? They decided to design all their offshore platforms for factor safety of 4. Because after they did an economic analysis, they saw that the cost of replacing that structure and all the lost income from having it down for a year and a half justified it. They saw that as you beefed up the connection details, you spend a very little amount of money and you get a big increase in factor of safety. And that's why you need to have engineers making those decisions, not accountants and attorneys. And that's what's happened in our country in the last 50 years, is the engineers are not making engineering decisions. The decisions that have to do with finances are getting made by bean counters, lawyers, and accountants who do not appreciate what factor of safety is. They couldn't even tell you a definition of factor of safety. But they're making the decision. And they're looking at the engineer saying, we don't need it that safe. Well, that's how people talk who haven't seen dead children. If you haven't seen a few dead kids, that's how you look at things. Cold, hard cash. Real easy to do. You need to get out and look at some disasters and realize a little more duct tape, a few more screws, those kids wouldn't be dead. Is it worth the 20 extra cents? You're damn right it's worth it, especially if you're one of the kids. So, how safe is safe? All right, well, I've done enough preaching for one day, huh? What's the next question? When are we going to get a break? When is this class going to be done? Okay. Well, let's see what we can go with today. I have some of this kind of stuff today, actually, for you. Let's see. All right. Estimating permanent ground deformations. I'm not going to make you an expert in this category. I just want to expose you to it, what the state of the art is in this area. It's come a long way. How would we estimate permanent ground deformations? Now, a lot of the panels I'm on are review panels. Things like for the World Bank, Asian Development Bank, Corps of Engineers, Bureau of Reclamation, Metropolitan Water District. The questions we generally ask is we look at screening analyses to tell us if we have this earthquake, which is the most probable earthquake in the next 30 years, 75 years, how much damage is it going to do? And do we need to spend money now to go out and beef up the structure, or can we wait till the earthquake occurs and then draw into our insurance pool? So that's the question you're asking most of the time. And so we have to have simplified methods to look at these structures and look at the deformations. How much strain am I going to get? Now remember, strain has an engineering definition. What is it? Do you remember what strain is?
The change in length over the original.
Right. Change in volume over the original volume, or the change in length over the original length. So it's got a very stated definition. So lateral spreads are a big worry. Lateral spreads were initially recognized here in Missouri after the 1811-1812 earthquake sequence. This is from Myron Fuller's 1912 USGS monograph. And Fuller wisely recognized that he saw these graben structures where you have a fault going like this, fault going like that, and the ground is dropped, and then these would be parallel and to a channel. And they would typically have an arcuate shape. So he was the first guy to recognize lateral spreads, and right here in the Midwest. And what he theorized was going on, that there was some quicksand forming down here, which is true, liquefaction. We're losing shear strength for a period of time, and the cohesionless soil, silt, sand, gravel, is behaving like a fluid without shear strength. And while that occurs, this whole mass floats over and laterally goes into some depression over here, usually a stream channel or an embayment or something. And so you can have very large tracts of land involved in these things. And Fuller recognized that they were always at depths of 10 to 20 feet deep. It was down some depth in the ground that these things were occurring. Well, this is the picture that Walt Hansen drew after the 1964 great Good Friday Anchorage, Alaska earthquake. And this is the picture you see in most of the textbooks, because you have this huge feature in Anchorage. This one feature alone was about a cubic mile of material. That's a big slide. And the escarpment going right through the downtown business district like this was a mile plus away from the nearest inlet. So this was a really big hunks of land that were moving around on discrete surfaces down here, and actually in this case on silt horizons. It wasn't even sand, it was silt, and large tracts of land moving. Now you got to remember, this earthquake, 2 to 4 minutes duration. How many equivalent cycles of loading is that? Well, that's way out there. You don't usually start seeing these kinds of features till you get past 5 equivalent cycles of loading. And of course in Alaska we're talking 40 to 60. So it's way up there. And you start having earthquakes of that duration, and you have saturated media with low cohesion, you're going to get lateral spread. So this is number one design problem right now in the Midwest. We're going to design an interstate highway bridge over the Mississippi River, whether it's down near Hayti, between Hayti and Dyersburg, or up here in St. Louis. Federal Highway Administration's coming in saying, how are you designing against lateral spreads? And the DOT's back here going, what be a lateral spread? You know, Walmart talk. What's that? We don't know what those are. We never even heard of that stuff before. Well, I better start learning about them. These are some very large loads you have to design your caissons for. Or you got to do something in here like sand or like stone columns to alleviate the liquefaction potential over a large zone. So that's a big design problem in geotechnical engineering. You got lateral spreads as bad news. And here's the one that everybody puts in all their textbooks. This is the Bootlegger Cove spread in Turnagain Heights, east side of Anchorage, the back side of Anchorage in 1964. And see, what it was a discontinuous series of silt lenses along the same stratigraphic horizons, more or less. So it wasn't sand. Sand was up on top. These were silts within a clay unit. Okay, and what happened here is when you have lenses, it's very important geologically. Because when I have lenses, I'm not going to get drainage. When I shake it, there's only one thing that's going to happen. The pore pressures are going to elevate. Lenses are just like a big Coke bottle with the top on it, and you shake it all up, and then you uncork it. Excess pore pressures all over the place. Okay? So lenses are bad news in earthquakes. Lenses are very, very, very hard to identify. If you bring a geotechnical engineer out here and they drill a hole here, they do a cone penetrometer sounding and they get silt here and they get silt there, they go get their ruler and they draw a straight connection between them like an interstate highway. Always, 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 always. They don't even know what the word lens means outside of going to get a pair of glasses. Lens crafters. So how does Big Dave know you have lenses? Not easy. Not easy. I have to be looking for them to see them. And I'd have to do enough cone penetrometer soundings in a small enough area to try and identify them. So not easy. Lenses are still one of the biggest geotechnical exploration problems we have in the business, even when you got smart people looking for them. So not an easy one to solve. Here's what happened to this. And by the way, this all recently got rebuilt. They put houses back on it because they need land in Anchorage. What happened is you get a lateral spread, you get horse grabbing, and everything just moves on over. And there's a beautiful aerial view of all this outside my office if you want to see one, taken by Chevron and given to their employees who lived in this area during the '64 earthquake. And Harry Seed was one of my co-advisors on my PhD thesis I worked for. He worked on this. And that was really his big, huge contribution in his career. That '64 earthquake jump-started him into geotechnical earthquake engineering, and that particular study was where he achieved his first international fame. Is there potential for lateral spreads in the New Madrid seismic zone? Oh, yeah. Yeah, they're all over the place. They just aren't recognized real well. This is a site that the Missouri Division of Geological and Land Survey trenched. They actually saw, it's north of Sykeston and the east side of Crowley's Ridge at a place called Holly Ridge. And they got in there, and it was a quarry. And when they got into the face of the quarry, they started seeing all this very active faulting, up to 9 meters of vertical offset in the Peoria Loess. Now, the Peoria Loess is all blown in just in the last 11,000 years. So that's definitely very active faulting. This is not even on the New Madrid zone. This is along the Commerce geophysical lineament, which doesn't even have any very much seismicity on it, active seismicity. This is what I think's going on at Holly Ridge. I think we're not seeing down deep enough to see what's going on down here in the stuff down beneath. But when you have lateral spreading out here somewhere, you start getting blocks that go up and down, and you get relative faulting between these blocks. And you get these little sand dikes that shoot up. And these sand dikes shooting up are just pervade Crowley's Ridge. Now, you want to see sand dikes, man, Missouri and northeastern Arkansas just are filled with these sand dikes everywhere. So this orange stuff is the stuff that's liquefied or partially softened enough that it's lost shear strength for a few seconds, and it's moved around, and then it's solidified up after it's bled off enough pore pressure, bleeds off enough excess pore pressure, it solidifies like concrete. Doesn't get quite as hard as concrete, but it solidifies, it has strength then. So this has to have shear strength in order to hold these blocks sitting here, because you have bearing pressure here. And then you get the Peoria Loess being blown in over that at the end of the glacial age, at the end of the Wisconsin glacial. So what you end up with today is something that looks like that. So that's one way you could explain that observation at Holly Ridge. So you can see here where doing good engineering geology is all about using the artistic side of your brain. You got to use your artistic side. You got to be able to sketch things like this and show them to your own people and to your client and say, here's one working hypothesis for this. Realizing it may not be the only one. There may be 3 or 4. We call that multiple working hypotheses. That is a central core aspect of geomorphology, study of landforms. You have to have multiple working hypotheses, because generally what happens is it's a combination of factors. that form the landforms we see at a site. And what's happened today in academia, we get all these experts in these little tiny areas. You know, we get loess experts, we got sand dike experts, we got worm burrow experts. And the experts, you get them all in a room, and what do they see? Everything is due to their particular expertise. What you got to do is crack their heads together like a football game and say, no, listen, guys, all this stuff could be going on here. Yeah, we could have the worm burrows, we could have the sand dikes, and we could have the loess. All this is probably interacting. So multiple working hypothesis is a very central aspect. You can't get away from that when you're trying to psych out and characterize a site. What things carve this site? One of the first things you got to do is get off that site, that's your client site, and look around the whole area to get an idea for the kinds of things that have shaped that site. Okay, what are some of the field identification things we look for with lateral spreads? Well, we look for saturated, cohesionless soils capped by low permeability materials, capped by things like clay and silt. Proximity to adjacent channels or some sort of natural depression. Prominent evacuation grabens, because as this thing pulls apart and moves away, it's going to leave a gap, a graben. That's how Fuller found the things. He saw this depression. He noticed that the depressions were linear. And then if you walked out the depression, it curved back toward the river in that direction, and it curved back toward the river in the other direction. And the light bulb went on in his head, and he goes, ah, this is a slope feature. But there's no slope, just flat. Boy, you get in your soil mechanics class, and they go, hey, you can't have any driving force here. It's just flat. Well, that's the thing about lateral spreads. They move on they're either totally flat to maybe up to 3 degrees. That's it. You don't have much slope on these things at all. So here's what they look like. This is another picture, this cartoon that I did. This is down near Helena, Arkansas. This is the St. Francis River, east side of Crowley's Ridge. And what we see is big, low-bait, pancake-shaped spreads that have pushed into the river channel. And the key thing here is they leave this graben, this depression that becomes a swamp. And it's laterally restricted. Laterally restricted means it stops right here. It doesn't keep going. It's laterally restricted. Gets thinner, thinner, disappears. Thicker, thicker, wider, deeper. And then thinner, 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 disappears. And then above this, you see these arcuate scarps, blocks, rotational slumping. We call this retroactive slumping. And when you see retroactive slumping, once somebody shows you what it looks like, it's very, very diagnostic of some kind of slope failure. So you have a horst and graben complex up here, things going up and down, up and down, up and down, because stuff is floated out. This is the liquefied zone right here in orange. See that liquefied zone? We have a pancake-shaped mass of material that's moved out into some depression, and we have the pull-apart depression here. So you have to have all 3 of these plus the channel down here. You put those together, and if they're laterally restricted, you probably have a lateral spread. You have to have a deep channel to move into. Now here is the geologic setting of southern Crowley's Ridge. And 50, 60 years ago, it was hypothesized that there's a fault, a bounding fault coming up on the east side of the ridge and on the west side of the ridge. Nobody that I know of has actually found those faults and confirmed that they're there, but everybody believes that they are because Crowley's Ridge is such a terrific topographic anomaly. And it runs for 240 miles from Cape Girardeau, Missouri, down to Helena, Arkansas. Long, long distance. And remember, I told you before that the Mississippi River flowed over on this side of it most of the time, and the Ohio River flowed over on the east side of it most of the time. So we get up here in the ridge. This is dissected Peoria loess sitting on top of Pliocene sediments on top of tertiary units, like the Wilcox Formation, the Claiborne Group, and the Jackson Group. Well, when I looked at the topographic map, I was immediately drawn. I just looked at all the topographic maps down in B12 one afternoon. And my senior design students can attest, I love looking at topographic maps. Some kids like listening to iPads. Other guys like watching pornography. I love to look at topographic maps. Okay, so turns me on. And when I was doing this, I started noticing these features, divergent contours, step topography, headscarp evacuation grabens, and arcuate headscarps in this area. These are smaller ones, and right here. So I said, you know, next time we go down there, Bridget Doyle was my grad student, I said, I really want to look at this one over and this one real carefully, because I think these are both lateral spreads along this old channel, this river channel along here, which is the Languisse River, which flows into the, right down here a short distance, it flows into the St. Francis River, which then the short distance down from that flows into the Mississippi River. So we went down there, and it didn't take long to figure out, sure enough, that's a big lateral spread feature, and here's that graben. There's the swamp that doesn't drain, where the groundwaters, or the water's right at the ground surface. You can't walk across it. It's just filled with water, and it's sitting right there where it's supposed to be. And then this thing in here is just a series of arcuate and echelon scarps that have been backfilled with Peoria loess. And you have this very sharp arcuate headscarp up here cutting through the crest of the ridge. So that was pretty neat, kind of exciting. And when you look at it in cross-section, this is what it looks like. Here's the Languisse River out here. This is the lobate part right here. There's the graben. And the graben tells you how far it moved. It moved about that far. And then these are the retrogressive slump blocks that came down into that graben. So this is a different style of land slippage than you have out here. This is just a big lobate thing that's cruising along on ball bearings, on liquefied ball bearings, and moving out into the channel. And what this is, this width here is basically the width of that river channel back in 1811, 1812. It was probably a little wider than it is today. But we had a very, very well-developed arcuate scarp right up here that was about 60, 70 feet high. That was pretty hard to get away from. So there's how much it moved. It spread, moved to the right. And there's the lateral displacement behind it. And then those are the retrogressive slump blocks. Now, I showed you this a little earlier. This is the one that we think is the largest of these features identified yet in the world. And this is actually down in southeastern Missouri, the advanced lateral spread. These are the Benton Hills. This is the Commerce Gap. The Mississippi River has recently blasted through this gap just in the last 6,000 to 8,000 years. And it used to flow down here and went through this portion here, and then before that it went all the way out here along the edge of the Ozark uplift. And this feature had been identified as a cutback from the Mississippi River, cutting it and then coming around. And that would be an easy conclusion to come to if you didn't know about lateral spreads. So there's what it looks like. And of course, one of the big dead giveaways is we got the subsidiary scarp right here, which is just as high, 9 meters, as this main scarp. Just an incredible, large feature. And so that was called the advanced crevasse splay. They thought the river broke through here at one time because all this drainage goes off in that direction. It doesn't drain back towards the river. Well, if we look at that, it's 67 square kilometers. One landslide feature. That's an enormous amount of real estate. It has a very striking headscarp. Let's look at that. If we look at these drainages here, these drainages are beheaded. So those drainages used to be going this way, and this thing dropped 9 meters, about 30 feet, and started moving that way. And this one dropped even more, dropped another 30 feet, and kept moving that way. And so you have a beheaded drainage, which is a dead giveaway. and then you have this arcuate scarp, and then you have a channel that has been displaced to the east and has a very flat gradient. Boy, you add all the things up, and you just can't come away but not thinking that's a lateral spread feature. So this one really bears having more research done on it. Why should we be concerned about these things in the Midwest? Well, guess where all the pipelines are that take all the natural gas and oil from the Gulf up to the Detroit and Chicago areas and Cleveland and on up. They're all going through this area. And here's the railroad line, which has pipelines going through it. So the railroad goes right through this thing, right over that scarp, right over the next scarp. That's the main line going between Little Rock and St. Louis. And so if you have pipelines coming across here, pipelines are going to get pulled apart in this thing. So there's where the original channel probably was. If we look at the river channel today is out here. That's how much it moved over, kind of in that sort of a direction. That's where the channel was at one time. It's been displaced a good kilometer and a half, and there's the flat gradient. Anytime you have a gradient like this, you either got two things. Either there's a dam right here, or there's some sort of blockage. This is a landslide, or it's a dam. There's no way you get a fall wag profile that looks like that unless you have some sort of hydraulic choke right here. So that's what's going on. That's why we run that kind of analysis. All right. How would I estimate the permanent deformations of features like this? How much is it going to move in a given earthquake? And that's what we get asked on these panels, and that's what you'll get asked when you go out in the consulting world, because your boss, the first thing they want to know is, do I have to go get some diamond stick pin downtown Chicago consultant to help us on this? That's going to cost $300,000. So the boss wants to know, do we need to do that? Well, so you run what's called a feasibility analysis or a sensitivity analysis to look at it and say, well, how bad is it? The Corps of Engineers decided for their levee systems and their earthen embankments that if you get permanent deformation of less than a meter, then you don't need to do anything about it. You don't need to go get a consultant and do a whole bunch of retrofitting because less than a meter of permanent deformation, soil's pretty flexible. It'll probably survive that kind of a movement. But if it's more than a meter, then you need to drop back and do something that's more rigorous analysis of it. So if we look, here's our problem. If I have a levee, like the Corps of Engineers is looking at, that's a nice system because it's all very mushy. And if it's all very mushy and it's homogeneous, when I have a big earthquake motion, whoomp, I'm going to spread that shear strain over a considerable distance and volume. If I put this stiff foundation, or this stiff material, on a soft foundation layer down here, if I have a little layer of silt or clay down here that's an inch thick, that's a bad situation. Because what's going to happen, if the modulus between the fill material and the foundation is very, very different, like an order of magnitude different, then this is going to behave as a rigid block, and all that strain energy is going to be taken up as basal shear right along here. So that little zone is going to feel a lot more traction shear. So that's where engineering geology is everything in this kind of stuff. It's just everything. Most levees are homemade, and they're not engineered. What does that mean? That means they come out there with some big old equipment, and they go, you want a levee here? You go, yeah, we want a levee here. Okay, I'll take whatever you got over there, and I'll go here, and there you go. Levee. Now, that's about how much engineering went into them. In fact, probably a little more. So what they're saying is they're taking native material from right here, and they're moving it the shortest distance they can possibly move it. So they're borrowing it from right here and piling it up right there. Now that's good for this kind of a model, because that means the stiffness between this stuff and this stuff should be what? dn squared. Damn near nothing. They should look pretty much identical. The only difference is this is going to be disturbed and has some sort of compaction, and you're probably going to get this thing settling under the surcharge of that embankment. That's the kind of stuff you should see. So when you drill in a levee, you're going to look for things like that. And you got to realize as you come off the levee and you go down here, you're going to see less and less and less and less, and down here you're going to see no impact of the surcharge. Now the big mistake they made that I criticized the Corps for, I got a lot of heat for it, but I had to make the criticism, even if it had been my brother or my parents that were running that office down there. They drilled the holes here and did all the analysis off these holes and said, this material has such and such a strength based on the tests we did. You can't do that. Why? It's called SU over P factor, P prime, pre-consolidation pressure. You have the most overburden sitting right on top of you right here. That's the strongest that foundation's ever going to be, is right there. But it gets weaker and weaker and weaker as you go out here. And out here you got nothing over it except air. So you have to take this number and reduce it by some measure that's significant if you're doing a slope stability analysis, and they didn't do that. They took the numbers taken right off the center line of the levee and used it for the whole cross-section. That would not have happened if they had had an external peer review board of people outside the Corps of Engineers reviewing it. And that's why you have to have external peer review boards of people who don't have ties to your organization. They aren't just retired from it last week. They're not tied to the organization, who come in and look at it from an outside perspective. And that's been proven over and over and over and over, and every single earthquake or disaster post-reconnaissance report I've ever read has that in the conclusions. Every darn time. And we still don't do it because we save money. 10 cents sometimes, 20 cents. You save money. We don't need external peer review. What we have is internal peer review. All right. That's what I like for traffic tickets. Internal peer review. Yeah, I was going too fast, but I didn't hit anybody. I didn't kill anybody. I shouldn't get a ticket. All right. Concept of shear strain. If strain is divided over a considerable area, you aren't going to have much strain. So that's the lowest. In simple shear strain like this, that's the lowest level of strain. But if I have a big stiffness change between this material and this material, or a big plasticity change, this is more plastic, this is more brittle, I'm going to get concentration of shear along that boundary. And this is the one you got to watch out for. This is the levee one. That's why levees do pretty good in earthquakes, especially if they got enough clay in them. Got enough clay, you're good to go. Natural slopes have stratigraphy. Stratigraphy has differences in properties and stiffness, and there's going to be your bane. Remember we talked about in rock mechanics? Dave's view of rock mechanics, very basic. It's all about differential strain. One thing strains more than another, you're going to have a problem. So if we go out and we look after earthquakes along steep-sided ridges like this is north of Northridge in the Santa Susana Mountains, hundreds and hundreds of little seismically induced rock slides. And when you go up and look at some of the larger slide features, you see something like this. I actually sketched this one in the Luzon earthquake in 1990. And what you see here is you see that they had liquefaction along discrete zones, and they have sand dikes coming up, but the whole mass only moved, a couple of meters. Now, we're going to talk about why that is. This is because of incoherence. Big landslides have big incoherence. Small little baby landslides don't have incoherence because they're small. So when you excite them, the whole thing just goes. It's like a body block on a sweep in a football game. You coming around the corner, you got acceleration, F equals MA, mass times acceleration, some poor defensive end standing there going, and boom, you can have a 165-pound guy blow a 350-pounder right off the field. Because force equals mass times acceleration. So that's why, when you're playing football, 2 steps on somebody makes all the difference in the world. Because it gives you some acceleration. 1, 2, bam! Hit it. But if you just stand there like this, hit somebody, you're not going to get anywhere near as much force. So, we're also going to learn about this kind of stuff. I don't know. So, what we do with all this stuff is we back calculate something called the yield acceleration, K sub y. Now, you run enough analyses of K sub y, especially after an earthquake, then you have some confidence in this number. But as I'm going to show you, this depends on the geology, the topography, and scale. But that's the way you get a comfortable feeling about K sub y, is doing back analyses. All right, there we go. There's a big-ass block, a BAB we call it. And that big-ass block did what? It went for a train ride. It moved. Now, statically, if I gave this to you on the final exam, this would be a great problem. I'd say, back calculate the phi angle for Uncle Dave. Geez, big heavy block. What kind of slope was it sitting on? PDF, pretty damn flat. Not much of a slope. What kind of friction do we got on that bottom of that block? Bath, big ass friction, big friction. So how did it get there? Don't all overwhelm me at once. Just one person answer at a time now. Huh? Earthquake, yeah. Something else going on here. I mean, we got something down here that lost strength, and we have some conservation of momentum issue here, because we're pushing this thing, and once it starts moving, this is a big, huge, intact block, and he's going to conserve his mass. His mass isn't disintegrating like a liquefaction failure. And this is the kind you got to watch out for. This is a liquefied seam, and you're just rolling along the seam, and the seam isn't getting any pore pressure dissipation because it can't get out, can't drain, so this block's traveling. And this is the kind of stuff you see in big earthquakes. And you just go, ugh. Frightens you. It's good to be frightened. Design things better. All right. So we go in to do a pseudostatic analysis, and we have some big, old, existing landslide, and that's usually the problem. We go out to some place like coastal California, 70% of the slopes in coastal California are covered with big, old, dormant landslides. And they build stuff on them all the time, especially in the old days when they didn't recognize they were slides. Or they look at it and they say, well, yeah, it's an ancient landslide. What does that mean? That means I don't have to analyze it. It's so old, it could never possibly happen again. And besides, my legal liability is only for 10 years. Do they stick the tongue out? Not usually. That's only when the lawsuit comes. 10 years. So do we have a long-term view? No. And it turns out they were wrong. A lot of these started reactivating in the 1980s. Part of the reason was in Hawaii and California, Oregon and Washington, they developed them, and they put in septic systems and leach fields, and they brought the moisture levels back up to where they were in the ice ages. And they started reactivating them. So we take them a lot more seriously today than we did 50, 60 years ago. Now, if I have an input motion here, peak ground acceleration, 0.4 G, that's 40% gravity, and say, okay, how much is this thing going to move around? That's a sensitivity analysis. So what we're going to do here is we're going to run through this thing and run a big event on it and see what it does. And this is the case we're looking at. It's called the Mission Peak landslide. And this particular slide I worked on back in 98, 99. It's about a mile long, drops 1,300 feet. Here's the crown of it up here. Here's the toe of it down here. It's about a mile long, coming into this neighborhood of Silicon Valley executives. Now, had an area of about 85 acres, 17 million cubic yards. How much movement is going to occur in an earthquake? Well, if we go back and look at it, this orange area is the landslide that reactivated in 1998. The yellow area is the landslide complex that had been mapped by various individuals back as far as 1958. 1958, they showed this area right here being in the landslide. 1994, a slightly larger area, and the big orange area, the big yellow area was 1994, and then this is how much of it actually failed in 1998. So if we look at that in cross-section, it looks something like this. We have an active fault coming up right here. All this strata is basically overturned. We have the landslide in here. We have a bunch of out-of-syncline thrusting, and we have a slide mass that looks something like this, and the active part is the yellow part right in here that we're seeing. Okay, so it's a series of coalescing earth flows, some of which are up to 180 feet deep, and individual lobes that are up to 900 feet long. So when you have a big landslide, it's actually a series of landslides. You have a lower part that moves first, and then a middle part that moves second, and then an upper part that moves third. So you have to divide it up into pieces to be realistic. So there's a real cross-section of the real slide. Here's the maximum thickness of 180 feet, so that's about an 18-story building. And so I have the biggest pieces of this thing were right up in here, and right here. And this one right here is the one that had the lowest factor of safety. So I ended up concentrating on it. And here's what that one looks like. And it's actually, there it is. And it's about 2,000 feet long. And then I have a section right here that's about 1,100 feet long. And then I have a very small one right here that's about 550 feet long. Now, this is really important, because these are some of the games consultants play. And they play a lot of games trying to be friendly to their clients. We call that being a client advocate. When you're advocating things for your client, the reviewer calls it being a whore, because you're not telling everything the way it really is. But client advocate sounds so much nicer than whore, and you make a lot more money than the whore does. But right here, if you just look at this guy, this is the one that's going to have the most movement, because it has the least incoherence. In other words, I can take earthquake motion, and that strong motion is going to be locked within this mass in a very short period of time, where it takes a longer time to travel up through this entire mass. So I can't have that 0.4 g peak ground acceleration on this entire mass at exactly the same time, unless I'm doing a pseudostatic analysis. So that's what's wrong with a pseudostatic analysis. It's only valid for small stuff, for rigid blocks and small slides, not for real-world stuff. But we use it as a screening tool to tell us if we have to do more sophisticated analyses. So it is valuable for that. So I know that in the end, this one's going to be the one that has the greatest deformation. And we're going to see that. I know that from the get-go before I even run any numbers. Okay, then what do? I have to do some sort of realistic modeling of the water situation. In other words, this is 75% of the slide mass is saturated. This is 50% of the slide mass is saturated. This is 25% of the slide mass is saturated. And when I do that, I get different yield acceleration curves. There's my yield acceleration curve at 1/3 saturated, 50% of the mass saturated, and 75% of the mass saturated. Now, I'm not going to test you on this stuff, and you're not going to see this on your final. I'm just giving you this so that I'm opening up a window and you can see what's going on out in practice. Now here's for the bigger slide mass. And you can see I'm doing the same kinds of things. And I'm getting very different curves. Why? Well, because I'm doing a rigid block analysis for the medium-sized earth flow now, and it's a different scale, and it's got a different geometry. And then here's for the overall mass. Now, when a client wants to, when a consultant wants to paint a nice picture, this is what they'll come in with. They'll say, well, Dr. Rodgers, we don't think we have a landslide problem here. You don't think you have a landslide problem? It's the biggest landslide in the Bay Area. Well, but we did some analyses, and we think you'll find this interesting. When we look at that whole slide, we don't get a very low factor of safety. Well, no, you don't. The bigger you make the slide, the lower the factor of safety is going to be, because of incoherence. So you got scale factors. So we do this one and we look at it, but you got to realize it's this little one right here on the front where you're going to get the failure. You got a house right here, you're hosed. That's what you're going to get decked. So we're looking at these things, we're backing out values, and the values we're backing out are the yield accelerations for these different sizes and different amounts of water. That's called a parametric analysis. And that's what computers are great for doing. Do I ever believe an answer I get out of a computer? Not on your life. Never, ever. The best we can do in the world of geotechnics is at like 150% strains. So I'm not going to believe everything comes out of the computer. What the computer is valuable for is to do a parametric analysis and to change these variables and see how much each variable tweaks the analysis. That's what's important. So you want to know, should I put in subdrainage? How much subdrainage should I put in? You can look at all those things and evaluate them. That's where it's very valuable, as relative assessments. Now, what's the appropriateness of pseudostatic methods? They use a rigid block assumptions. And those should not be used to model earthquake-induced movements of large, dormant landslide complexes. Okay? They work great for this kind of stuff. Sliding blocks, go with Newmark. Will you get a good answer? Yes. We know that from back analysis of block slides, small block slides, and earthquakes all over the world, like Northridge. But those are small earthquakes and small landslides. That ain't the kind of stuff that does huge property damage. And so it would even work for a small rotational failure like this. When you get out into the real world and you have blocks and flows and things that are larger, it doesn't work as well there because things are much more nonlinear. Okay, so here we are flying around the Santa Susana Mountains just after an aftershock on Northridge, and what do you see? You see dust just flying up all over the place. That's because of this flagpole effect on these very, very steep-sided ridges. These ridges are steep. They're all up around 40, 45 degrees. That's very steep. So when you get something that's steeper than 40 degrees, you're going to have very significant topographic enhancement. That's what you would expect. Here we are flying along, looking down on that. A couple weeks later, we're up higher now. We're on a commercial flight coming from Oakland into Burbank. We fly right across this ridge. I look down the ridge. That's a knife-edge ridge on the Santa Susana thrust. And notice something. I see a whole bunch of failures going to the right, but I don't see them going to the left. That's real typical of earthquakes. What's going on here is you're in the hanging wall block, the Santa Susana thrust is down underneath you here, and what you're seeing here is this thing getting punched by vertically propagating shear waves coming up at an angle like this, and so this side of the ridge is really getting blasted, but you don't see it over on the other side of the ridge. That's pretty typical focus effect, called focal effects, that you see from topographic enhancement and the directionality of the incoming seismic wave train. Vertically propagating shear waves are the worst for liquefaction and for slope failures. And you're going to get more of those when you have a reverse fault or a thrust fault. And so strike-slip faults, not such a bad deal. Strike-slip faults, everything's horizontal. Much, much nicer, less complicated, easier to analyze. When you have a reverse fault motion with high vertical component, you get a lot of this kind of stuff. Now, Newmark, by the way, analysis works great on all these. Analyzes them. Randy Gibson at USGS analyzed all these slides in the Santa Susana Mountains. He had an incredible fit between, you know, what they saw and what he theoretically backed out of all of it. It was an incredible fit. It was way up in the 90 percentiles. Okay, so if you want to look at these masses and estimate how much they move, one of the first things you got to do is estimate the fundamental period of the slide mass. This could be a sanitary landfill as well. You characterize this thing, you say, what's the characteristic period of it? Characteristic period is going to be 4 times the depth divided by the average shear wave velocity. That's pretty easy to back out of it. That's what you need as the first calculation to do any kind of analysis. Then you're going to look at impedance effects. Now, impedance is this shock energy that's coming up through the bedrock, which is nice and hard. And as it goes into something soft, it can't transmit through the soft stuff as fast as it's transmitting through the bedrock. Now, here in the Midwest, their impedance factor, as I told you last week, is sky high. It's somewhere, you know, the shear wave velocity down here in the bedrocks between 1,400 and 2,800 meters per second. That's faster than bullets. That's just incredible, because we don't have a busted up crust back here. So you look at the average impedance ratio in the Peoria loess and the superficial materials we find back here, post-glacial materials, 165 to 185 meters per second. So big change, 25-fold. I never saw anything approaching those kind of numbers working out in California. Nothing close. Not anywhere. Not in Yosemite Park. You don't get anything that close. So you have this contrast. Think of it like this. If I have shear wave energy coming up like this at 2,000 meters per second, and it gets up into something that can only go 180 meters per second, what's going to happen in 10 seconds? You're going to have 25 times as much energy coming up into this thing, more than it can transmit through it. So you're going to store that energy and magnify it because of impedance contrast. So that's your big enemy. That's how you have to think about things. You have to think about things as a dynamic system. You got to think like back when you use civils, you know, go back to structural analysis, fundamental course, civil engineering, structural analysis. That's how you have to look at it. Look at that. Doesn't that look like structural analysis? The impedance ratio is the density of the foundation times the shear wave velocity of the bedrock. That's two same things down here in the gray, divided by density of the landslide times the shear wave velocity of the landslide. So now you have vertical incoherence and you have lateral incoherence. A lot of people, again, forget that. This is very important if you don't have strike-slip faulting, which we don't, you know, in the Midwest we have strike-slip faulting on the New Madrid, and the real foot rift is a reverse fault. So that last big earthquake we had in February 1812, the one that blocked the Mississippi River for half a day and lifted things up 20 feet, that was so devastating because it had a very high vertical component, created real foot lake. So here you look, vertical incoherence is the upward component of seismic energy. It travels through the slide mass. It's going to alternately compress and dilate as that wave train moves up, just like this. It's going back and forth, but it's coming up like that. So that what that means is I'm going to have one load right here and something different right there, right there, right there, right there, right there. Now, we do pseudostatic. We just put the same load on it all at one time. We ignore the dynamics of the whole thing. And that's fine as a screening analysis. It's just not real accurate. Now, here's where you get in big trouble. Lateral incoherence. Back when I went to school in the Stone Age, we'd look at all these huge landslides up in the San Gabriel Mountains and the San Jacintos and the San Bernardino Mountains, and my geology professors would all say, well, you know, we live right on the San Andreas Fault and the San Jacinto Fault. We got all these big, huge faults. So all these giant landslides we see, they're probably all seismically induced by earthquakes. And we all grew up, oh, it's gospel truth. That we all believe that. Well, then we had an earthquake, 1971. San Fernando earthquake, mag 6.9, 6.7, 6.9. Then we had the Northridge earthquake, same, around 7.1. And we didn't see all these landslides reactivate. What you find out about landslides is the water table has to be high, and the focal effect of the motion has to be coming from a certain direction to trigger them. So you might have 10,000 landslides out there, and in a big earthquake, 100 of them will get reactivated. You don't see all 10,000 all get reactivated all at the same time. That's a myth based on a lot of nothing. So what you see here, the larger landslides don't typically move as one big, huge unit because of lateral incoherence. So now I got this seismic wave train. These are horizontally propagating shear waves. This thing's coming through like this, and you can see you're going to have a peak ground acceleration here, but not there. Another one here, there, not there. Another one here, not there. And so that wave train is traveling through the slide mass. So when I got over to the Luzon quake, we had a huge earthquake in the Philippines, and I knew that northern Luzon was just blanketed by huge landslides on altered ash beds. And they're in the tropics. They get big moisture levels. So I was expecting to see huge detachments. Never saw one. Big, huge earthquake. What did I see? Lots and lots of little headscarp movements up here that were 1.5 to 3 meters. And the reason is the slides are so large, they go out so many kilometers, there's no way you can have that large acceleration uniformly applied to this entire slide mass at the same time. You have a bunch of body waves traveling through the thing like this. That's what's really going on. That's the dynamic system. And we can model those things with computers, but it's expensive. All right, so what do? Screening analysis. We take the maximum horizontal acceleration. We look at the window of duration for different magnitude events. We back out our duration. And then we look at the mean period of the acceleration, time history, and we look at durations of that. And we're going to use these factors to go to this chart, which looks at the normalized maximum horizontal equivalent acceleration at the base of the landslide. And it's normalized. It's divided out. So we came in here. We ended up in this zone. This is data from earthquakes around the world. And we're going to look at it here as at normalized fundamental period. So we see here's our band. We're going to be somewhere in there. And if we take the mean, we're right about here. And that's where I brought my line down. And you see my ratio is just about 1. So the T1 of my landslide versus the natural period, they're about equal. That's pretty interesting. That's just coincidence that it worked out that way. Then I go to this procedure where I'm going to look at the yield acceleration divided by the maximum acceleration, and I'm going to go through a series of simple range calculations because I have nonlinearity. I go to this chart, which is a normalized based sliding displacement versus that ratio I was just showing you. And in this particular case, my zone is right in here, and I come over to here, come down, and there's my numbers go from here to there. So there's my range. That's the range I'm going to be in. In this case, for this is for a 2D analysis, it was 0.63 to 0.88. So the displacement I'm going to get is going to be between 1.5 meters and 1.5 and 10 millimeters per second on the basal rupture surface. So the expected range of permanent ground deformation I calculated for this one was 3.6 to 33.6 millimeters, which is well below a meter. So that's a third of a meter, not not even that. It's 3 centimeters. Not a big deal. So when we got done with this whole thing, here's what I ended up finding out. Sure enough, the one out here on the front has the most likely movement, somewhere between 2.5 and 9.5 inches. This one, the scarp will move 0.2 to 1.3 inches, and up here, 0.2 to 1.5 inches. And that's exactly what you'd expect. And that's the kind of stuff that you see when you go out after an earthquake reconnaissance. You'll see the smaller ones detach and move a lot more than the bigger, deeper masses that are longer because of lateral incoherence. So that's what I wanted you to get out of this lecture. So Newmark method gives an adequate evaluation for superficial rigid blocks, but the Berkeley simplified method predicts permanent ground deformations generally increase with the decreasing size of the landslide mass. If the movements are greater than 1 or 2 meters, then you may need to do a site-specific dynamic analysis like Quad 4 Pro, something like that. It's going to be much more expensive. All right, we'll take a little break right now and then go on with the next lecture. we on yet? Guess we're not. And so I went to St. Louis, and leading up to this, I had months and months of phone conferences with different members of the Federal Reserve Bank system, talking about the things that interested them and could I address these things. And so that's why you're going to see me talk about the kinds of things we're going to talk about here. And I think this is a good door just to kind of crack open for you to realize that these are the kinds of dialogues we should be in as an engineering community. We'll start here. Peril breakdown of insured losses. So insured loss statistics, what are they based on? They're based on what's occurred in the United States over the last 100 years. And that's going to be statistically biased towards the events that occur with the greatest frequency. So I'm not going to see things that don't happen very often within a 100-year period, like 100-year floods, true 100-year floods. I'm not going to see those because what I'm going to see are the things that happen all the time. Now, notice here, what's the biggest single area in terms of property damage? Property damage is based on what people take bank loans out for, because that's where we lose a lot of money. If your house gets blown away in a hurricane and it's gone, are you going to keep making the house payments for the next 27 years? You all laugh at me. Your banker's just going to get stuck with that. Oh, the rest of the depositors at the bank are who's going to get stuck with it. That's who gets stuck with it. So yeah, so hurricanes are the single biggest arena over the last 100 years, 44%. And this doesn't count the biggest hurricane in our country's history, which is Galveston in 1900. Galveston's not included in this. And that's also the biggest storm event we had in Missouri, was the Galveston hurricane in 1900. Still the storm of record for Missouri, as well as Oklahoma and Arkansas, and a lot of other parts of the country. Okay, the narrow fringe comprising 17% of the contiguous U.S. land has more than half of the nation's population. So 17% of the country has more than half the population. Between the years 1980 and 2003, population of coastal counties increased by 33 million people, or 28%. This is a very significant number I want you to think about. In 2003, 23 of the 25 most densely populated counties were in coastal areas. By 2008, over half of the American population lived within 50 miles of the coast. Now, we know this when we do faculty recruiting here. We don't get many people from either coast. People on the coast want to live by the coast. We get mostly people from the Midwest and people who want to get a green card real bad, okay, and aren't party animals. All right, so what is that saying? Are we parking ourselves in an area of greater risk? Yeah. People got off, 90% of the population 115 years ago were on family farms. Today, less than 10% of the population is on farms. I mean, it's not even 7%. In fact, you can even get the farm tractors now to drive themselves with GPS. You don't even have to be there for it, I guess, other than to turn it on, turn it off. So for the people in the coast, wow. Now here's, tornadoes. Tornadoes and hail. Hail got my roof this last year while I was gone. Had to have a roof replaced, $23,000. That's a very real one. And that one tends to stay pretty constant. This is earthquake. Now the big problem, as we're going to see with earthquakes, is earthquakes come without any warning at all. So we're going to have half the people are going to have less than half a tank of gas in their car. They're not going to have the options that somebody else has who has a full tank of gas in their car. Nice thing about hurricanes, nice thing about floods is, and tornadoes generally, is you have some forewarning. Winter storms, all the rest of these guys, the two exceptions are terrorism and earthquakes. We don't have any warning. They just hit you. And they're boom. So they have big shock factor in them. All right. Now, we look at where earthquakes are. Earthquakes are along the suture zones. Most of the earthquakes are at boundaries of tectonic plates. New Madrid, big exception. Yellowstone area, another big exception. So most of the world's earthquakes are along these major tectonic zones. This is just looking at earthquakes from 1960 to 2010, 50-year period. All right, earthquake frequency versus magnitude. The higher the magnitude, the less the frequency. But a magnitude 9 earthquake is equivalent to about 172 million tons of explosive. Wow. So the largest nuclear weapon ever tested was detonated in the Soviet Union, 1961. That had a yield of about 50 million tons of explosives. So equivalent of a magnitude 7.7 earthquake. And in fact, that's how we monitor all these things, with the seismic network. That's not hard to do. So we look at San Francisco, 1906 earthquake, right there. New Madrid event, bigger event, notice. Wow. Look at some of these. Chile, 1960, way up there. Alaska, 1964, order of magnitude bigger than the San Francisco earthquake. Pretty interesting how these things spread out. So there's the nuclear explosion there. Novaya Zemlya. Typical variation earthquake activity since 1895. Earthquakes are very, very cyclical. This is the bad thing. This is what's very hard when you're talking to a client. In California, I used to always have the one I hated was coastal retreat. I did a lot of dispute resolution work for the California Coastal Commission, because they have a law that says, you can't have your structure closer than 75 times the average rate of coastal retreat. So if the average rate of coastal retreat is 1 foot per year, the closest you could put any structure to the top of the bluff would be 75 feet away. And of course, people want to be right out there a little closer. And I would get into all these battles with clients, people, very wealthy people usually, and they'd say things like this: I've lived here 27 years, a lot longer than you've been here. You've only been here 15 minutes, and I've never seen anything erode off that bluff. Now, what do you say to that? Goodbye, I'm going home. See you in St. Louis? Huh? What do you say?
Not much of an observation period.
Yeah. See, the thing is, every year they're sitting there, there's a greater likelihood that that cliff is actually going to have a movement sequence. When you go back and look in the aerial photography on California coast, what you find is it's very episodic. What does that mean? That means every once in a while, typically every 30 to 40, 50 years, there'll be a sequence where you'll get a lot of rain and you get a lot of storm activity, and they coincide in a way that you get a sequence of cliff regression. So all of a sudden, 30 feet of cliff just goes overnight. And it sits there for the next 90 years and does nothing. But that cannot be appreciated in a human being's time frame of observation. They can't appreciate the risk because they haven't seen the dead child yet out in the floodplain or in the building, see? So if when you go out and you look at disasters all the time, you become very hardened like a cop. And you just say, well, this is easy, you need to do more. But if you sat there and you've never seen the devastation when somebody losing everything, then it's hard to appreciate. Now, the problem you have is statistically, look at this. Whole bunch of activity, very little activity. How much are we going to worry about earthquakes right about here? The answer is not very much. What's going on here? What's this horny-looking thing? Huh? that too much testosterone? What is that thing? That's the Chilean earthquake in 1960. That's a magnitude 9. Big energy release. So big, basically, it biases the whole chart. If I didn't have that thing there, I could show these as being much bigger features over here. So that thing, and we have another one of these with the Andaman Islands earthquake right here. Didn't quite show up quite as big. So right now, we're going back into a period of relatively high seismic activity. That's typical of the cyclical nature of natural systems. And that's bad for us as a democratic culture, because we like to plan for things and we like to budget a flat budget for stuff. And that's not how catastrophes work. They don't work with flat budgets. You can go along for years and not spend much, and all of a sudden you start having a lot more activity and you're going to go bankrupt. And that's what's happened to us with since 2005. Where the National Flood Insurance Program was bankrupted by Katrina and Rita. It still is. So, is the apparent increase in earthquake activity since 1994 relative to the period before, is it just a coincidence? Well, it's just part of these natural cycles that we have. And right now, we're in a higher earthquake cycle than we were in the 16 years prior to 1993. So let's look at hurricanes. Hurricanes in the North Atlantic. And we didn't have any hurricanes come north of Cape Hatteras prior to 1935. That's kind of interesting. So there is a pattern shift. Of course, we haven't watched it for for thousands of years or anything. But what you actually see here is, you see there's a cycle in these things, a relative cycle. And yeah, we are in an upswing right now. And it could go down, it could stay up, stay elevated. So there we are prior to 1960, mean hurricane, standard deviation, and there it is since 1960. Now, what's bad about this chart is, where did all those people move to the coast? Down here. You got more and more people moving into this zone. At the same time, you had higher and higher and higher risk. And this is what's bankrupted the banks, because the banks' actuaries just plugged through one mathematical equation. And it's the mathematical equation based on how many trains I've seen go by, going back as far as I can see. So they're plugging all this data in to their risk models. And those are not good data for predicting where they are right now. They're way above where they've ever been before. Way above the maximum where they've ever been before. So in this case, using that actuarial data to look at your risk for a homeowner's mortgage, it's going to get you the wrong answer. You remember we had this stuff when you took basic physics? What do we call it? Skewness? Remember the term skewness? And what was the other one? There's another term too. Cirrhosis or something. This for how something's changing rapidly. Well, look at that line. That's changing rapidly. That should scare you if you're in the mortgage business, because it's going up. Like that. All right. Now, over the last 200 years, Missouri has experienced the largest earthquakes in the lower 48 states. But I would also say to you, 200 years isn't very long at all. All we have to do is look at the Christchurch, New Zealand earthquake we had back in mid-September. That surprised everybody. Why? That fault was thought to be an ancient, dormant fault. They hadn't had an earthquake on that fault in 16,000 years. The active fault on the South Island of New Zealand is over on the west side of the island. Christchurch is over on the east side of the island, the opposite side of the island. So they had this magnitude 7.1 earthquake right underneath them. And it was kind of like Port-au-Prince for Haiti, and they didn't expect that at all. And nobody was killed. Partly that was the timing, being 6:15 in the morning. But If they had people had been at work, they would have lost some people. But that just shows you the problem we have with natural systems in that we haven't watched them long enough to be a significant sampling. So what does that mean? What does Dave want you to learn about all this? Here's what I want you to learn. You ready to write down? You're always going to get surprised by natural perils. You're always going to have things happen that have not happened previously. So what's that do to your actuarial calculation? It means it's always going to be wrong. Now, this really worries actuaries. And when I got into this with the Federal Reserve, we got into a very spirited discussion. Believe me. Very spirited discussion. Because what scares the insurance industry is something they haven't accounted for that's big enough to do what? Bankrupt them. That's what they worry about. That's what they lay asleep at night worrying about. Did we miss something here that could bankrupt us? Okay. And what you want to do in something like this, you can say, well, we got this earthquake risk here. We want to spread this to as many households as possible so that we don't go bankrupt. And give you an idea, Allstate Insurance, after Hurricane Katrina and Rita, they pulled out of Louisiana. They said, been there, done that, had enough, we're out of here. You know, we've had one after another, after another, after. They just had Ivan in 2004. The next year they had Katrina, and they said, we've had enough, we're out of here. They pulled out. It's the first time that one of the big 15 largest insurers in the country had just said, we're not going to serve that market anymore. We think the risk is too high. Now here's the National Earthquake Hazard Risk. We asked FEMA, what's the risk? FEMA has fairly simplistic models. These are based on assumed soil thickness of about 100 feet over the bedrock, so it's not real detailed. These are by counties, this coloration. But here's this zone down here, which doesn't even really take into account the Wabash Valley seismic zone right up in here. And so we have this earthquake risk in here that's never been tagged previously. What's tagged mean? It's basically like me telling you, you live in a hurricane zone, but you never had a hurricane. So how prepared are you going to be? You're not. You're not going to be prepared. Ain't nobody's going to, there's very few people who are going to be really prepared till this thing goes down. And then everybody's going to say, why weren't we, greater prepared for us? Why didn't FEMA take care of us? Well, FEMA's got 4 regions coming together right there. So that's really going to be interesting, as we're going to see. All right, paucity of data. Paucity is a big English word. It means don't have much of it. Paucity. Don't have much data. What do we have? We got one significant earthquake sequence 200 years ago when nobody was living west of the Mississippi River. So we got these isoseismal lines all the way across the eastern United States. Hey, we're ringing church bells in Boston, way out here. What? Yeah. What happens over here? Well, you're safe over here. See, there's no lines over here. No data. There's no data over there. Native Americans did not keep their data. They shredded all of it when they signed these treaties. That's a joke. Dave tells you jokes. Okay, so this is modified Mercalli index. That's what we had back before we had seismographs. So did you feel it? Did it knock your chimney over? Did it knock the building down? Did it knock you to the ground? Et cetera, et cetera, et cetera. All right, so where are the active Midwest seismic zones? We know New Madrid's active. We didn't even start instrumenting it till 1974. Why? Because somebody came in here and wanted to build a power plant in West Memphis across the river from Memphis. And to do that, you have to process an application about this high with the Nuclear Regulatory Commission. And the Nuclear Regulatory Commission has the most conservative, stringent seismic design criteria of any regulatory agency in the world. So they're tough. And they look at earthquakes for design purposes that are 500,000 year earthquakes. Occur every 500,000 years. That's very, very conservative, because the word nuclear, just scares a lot of people. And so they didn't even start looking at this till they went to process that power plant thing, and then they got into the, the geologic records, and they found this report by Fuller of the USGS back in 1912. And they go, earthquakes. So that's how it started. And that got the seed money to put the seismograph network down here to get a good feeling for what's going on. So we only got 40 years of data, coming up on 40 years of data, not even at 40 yet. And then in 1999, seismologists decided we have this Wabash Valley zone. Now, these are all historic earthquake epicenters we're showing here. All these dots all over the place. So we have this zone that's recognized. These are just not recognized. They're amorphous. They're outside the zone. And we have the Wabash Valley zone. We think that it spawns a magnitude 7 earthquake probably every 1,000 years or so, but we don't really know nearly as much about this one because we don't have the kind of a net on this one. All the instruments are down here. And then we have this amorphous zone, which I call the South Central Illinois Seismic Zone. I can't say that inside the state of Illinois, or they'll try to assassinate me. They say, you can't call that, you can't call that, that has not been decided, that is not, go away. Go away, go away, go away. Well, their quakes are there. So you call it what you want. I call it the go away zone. The go away earthquake zone that isn't going away. Got some big quakes in there. And so these are the source zones that we know very little really about them. The problem with South Central Illinois, by the way, is it's underneath 400 feet of glacial drift. So you can't go down there and look at the bedrock there. And that's why it still hasn't gotten decided on. Now, last good-sized earthquake was 115 years ago. Halloween, 1895, centered in Charleston, Missouri. It's way down in the southeast of Missouri, not too far from Cairo, Illinois. And this, I showed you the Cairo Bridge last week. This earthquake affected, shaking intensity, it affected an area 20 times the size of an equivalent size earthquake would affect in California. Wow. Wow, 20 times. 2 times would be a big number. 20 times is unprecedented. So that's a big problem. Here's the problem. I showed you this last week. The problem is attenuation. Energy does not attenuate or lessen with increasing distance very much in the Midwest. So what's Dave's conclusion? Don't use charts generated with seismic data from California, which is just about everything. Just about everything we have, those things I was showing you before, all those charts I had with all that data for estimating the landslide, that's all California data. So, not real applicable to being used back here. You can't use attenuation versus distance and magnitude versus distance data that's out there in the data pool right now for the Midwest. Doesn't work back here. All right. The other big problem is that shaking intensity varies from one area to another. So where you live, where you're parked, has a huge impact on how intense the shaking is going to be. So I get the calls all the time. Every time I get quoted in the paper, I get about 3 dozen calls saying, and here's what the caller says, Dr. Rogers, are you the earthquake expert? I am the earthquake god of the world. Ask your question. Do you have a cashier's check for $500? No, I don't say that. I usually try to answer the question. But what's the question always, Emmett? Should I have earthquake insurance? I could save $25 if I didn't have earthquake insurance. So if you're on bedrock, you live in Rolla, you probably don't need earthquake insurance. All right. So I showed you this last week. Seismic site response. Whether you're on the hills or you're on the floodplains, it makes a big difference in terms of how much the energy is going to be magnified. I showed you this as well. You're on the rock, you're going to feel a lot less shaking than you're going to feel being up on top of the alluvium. If you're up here on top of the bridge, you're going to feel even more because you're going to be that much higher above the ground, so you're going to have the structure moving around in excitation relative to the foundation moving around. And when you look at these things and you look at the spectrum on the rock versus what you're going to feel on the ground, it's a huge difference. And it's the biggest impedance contrast of any place in the world. And this is, I think I showed you this last week too. This is just looking at the difference in spectral acceleration with depth of the soil cover, the alluvium. And the deeper the alluvium gets, the more this shifts over, so that long period motion becomes more and more important. And that's very important to us in St. Louis because we're at 200 kilometers plus from the source area, so we're going to get long period motion from the New Madrid or the Wabash zone. They're about equal distant away. So that means it's the structures, 0.8 seconds and above, that are the most vulnerable, the long period structures, tall or long structures. So we see, I showed you this before last week too, on the bedrock here, you're not going to get shaken too badly. On the shallow cover, which some of St. Louis is in this category, by the way, the shorter buildings are really going to get rattled big time. The 2 to 4 story stuff, especially East St. Louis, that kind of area, really going to get the heck shaken out of it. But the longer period structures are the ones that are going to get shaken out in the deeper alluvium. So when you look at this stuff, 0.2 seconds spectral acceleration, that's like for a 2-3 story building. That's the kind of stuff that we cover in the building code. The building code basically covers up to 3 stories, wood frame with nails and shear walls. You do everything like the building code says, you're going to get out of the building alive. The building might take some, additional damage. The building might burn down on the fire that occurs after the quake because the fire mains are compromised by lateral spreading. That's what happened in San Francisco in 1906 and in 1989. In fact, the sad thing about San Francisco earthquake, I told this story to the Federal Reserve Board. After they had the earthquake and the city burned down, they said, how can we make this safer? Let's have a panel of experts. That's always the thing to do. So we'll get 2 professors from Berkeley. We'll get 2 professors from Stanford. We'll come in and we'll say, professors, make it so we don't knock all these buildings down and kill 5,500 people again. So the professors turned in their report, and they suggested that the structures be designed for an equivalent wind loading of 40 pounds per square foot. Now, usually we design wind loading for about 15. And so when they started to design buildings, they said, oh, this is going to cost too much money. We can't get the bond financiers from New York and Boston and Philadelphia to give us this much money to build a building. They're saying, it costs too much money. They can build it for a lot less than that in Memphis or St. Louis or Salt Lake City, some other place. So what they did is they rescinded the building code they passed in 1908. Took out the seismic tenets. Well, how do we couch for that? Well, the reason the whole town burned down is because the fire mains were compromised. So let's make the fire mains so they won't be compromised. So they brought in engineers on this one. And the engineers looked at it and they said, well, the place where you lost the fire mains was at 7th and Howard, 3 blocks south of Market, in a made land area, an old inlet on Yerba Buena Cove. So what we'll do is we'll put a redundant system right down the middle of Market Street. So they tore up Market Street and put in these 2 parallel fire main systems, and they had emergency crossovers, but they were locked off. So now they had a separate system south of Market Street and north of Market, because north of Market Street they got the hills that had the big fire storage tanks, the water tanks in them. And if you break it at 7th and Howard, you don't want to have these tanks all get drained out through that. Oh, that's what happened in 1906. That's why the town burned down. The fire didn't even start for 5 hours, 6, 7 hours after the earthquake. So that's what they did. No seismic code, but we have a redundant firefighting system. That was in 1910. Well, along comes 1964. And who remembers 1910? They didn't even have cars in 1910, hardly. They didn't have television. They didn't have radar. They didn't have any of the great things we have today. And so they were getting ready to build the Bay Area Rapid Transit District, and they had this Tenderloin area down at the foot of Market. It's really sleazy, a lot of sleazy, bad stuff. And they wanted to reinvigorate that and get it built up And so, in fact, they didn't even put a BART station in down at the bottom because it was so bad down there. And so they decided, well, we want to do something to stimulate redevelopment of this bad area. And so that's what they started doing. And pretty quick, they ran up against Uniform Fire Code, UFC, which says, if you're going to start building high-rises down here, you need this much water. And you don't got the water for fighting the fires down there. Oh, no. Oh, we didn't see this one coming. What are we going to do? This is just killing us. Here we're trying to make a better place to live in a better city and get rid of the Tenderloin area and bring in some nice, high-rises and a Hyatt Regency Hotel and all this thing. We got to do something. Let's get put our heads together and see what we can do. And the fire chief told them, well, we got this redundant firefighting system here, And so some person said, I know what we can do. We can open up these crossovers so we can effectively double our firefighting capacity on either side. They probably didn't think of that back in the old days because they didn't have television or anything, Didn't listen to the radio even in those days. So they opened it all up and took out the redundancy. So when the Loma Prieta earthquake hit in 1989, which wasn't even 1/35th as big as the 1906 earthquake, okay? It was about 1/25th as big. Where did the San Francisco water main system get compromised? At 7th and Howard. And it drained the entire city's firefighting capacity. Welcome to the world, kids, where Dumbos blossom like bacteria every time you turn around. There's somebody who runs a city or a state or a county who doesn't know jack bananas about the history of the place they live in and makes an ill-informed, stupid, moronic decision like that. And San Francisco would have burned to the ground in 1989 in the Marina District because they had no firefighting capacity, and they had all these natural gas lines on liquefied made ground that had been built in 1915 for the Pan-Pacific Exposition to celebrate the rebirth of San Francisco. So they put it on made ground, the made ground all liquefied. They lost the fire mains. They had no fire water in the tanks because the tanks drained through 7th and Howard. There's only 6 nights a year in San Francisco where the wind's not blowing, and October 17th, 1989 was one of those 6 nights. Otherwise, the town would have burned down again. Wow. So that's the kind of stuff you go up against as an engineer. And you better know your history. Because I came out with this stuff, and boy, I got called a lot of names. I even got called some bad names by some famous people until they found out I wasn't making these stories up. And one of them, who was a National Academy member, he said to me later, when he kind of apologized to me, he goes, I've been around here 40 years, and I never heard these stories. Yeah. They don't make it onto the evening news or on the halftime at the NFL game. Or even they're not even on the PGA Tour. I mean, you have to go to the library and crack open some books to read about them. All right. So, what are future earthquake hazard maps of the Midwest going to look like? They're basically going to look like this. They're going to track the channels that have the alluvial sediments that magnify the earthquake motion. And these are your areas that have much greater risk. Here's Crowley's Ridge, see? That's nice. That's the place to be. Be up on top of Crowley's Ridge. You get a better view anyway. And you're not going to be nearly as much at risk for... you do have seismically induced landslides up there. Just get back off the top enough. But that's what the future maps are going to look like. They're going to be along the major river channels. Does that mean you don't get any shaking in here? No. You're going to get shaking in here. It's still going to be serious in some of these upland areas for the 0.2-second spectral acceleration, but not for the long stuff, not those real big peaks. They're not going to be a big issue for you. All right. Well, this is the most likely earthquake we expect, the magnitude 6 to 6.8. What if that earthquake happened tomorrow? What would get whacked in St. Louis in a magnitude 6.5 earthquake? Well, basically structures sitting on alluvium deeper than about 50 feet. Structures or improvements on filled ground where the alluvium thickness is greater than 50 feet. Taller structures, i.e. greater than 7 stories tall. Embankments placed on unconsolidated alluvial materials. A lot of this over on the Illinois side of the river in the floodplain. And tall structures situated on old soil-filled basins. And we have a lot of that actually out by the airport, but we don't have any tall buildings out there. So the airport's got a big basin there about 150 feet deep. It's an old lake basin, a bunch of lake sediments. What are the critical infrastructure that we need to worry about? Well, it's the multiple span bridges, as I told you last week. In particular, it's the tail spans. It's the approaches. And the one that's got the government most worried is Poplar Street Bridge, built for Interstate 55, 1967, 68, because all the fiber optic network goes across that bridge. I'll be showing that to you. The buried oil, gas, coal slurry, water, and sewer pipelines crossing the floodplains are all at risk. That's the single biggest effect. The high voltage transmission lines crossing those floodplains also at risk. The power plants that are situated along the major channels are going to go down. And that's a big factor for us because that's most of our thermal plants are located along the major rivers. And water treatment and sewage treatment plants along the channels, all of them are along the channels, and underground storage tanks. Now, what is the non-critical transportation infrastructure that could be affected? Well, barge traffic. That's a big unknown. Depends what time of year, what kind of year you've had when that occurs. The fuel pumps are going to be made inoperative by the loss of electricity. This is the single biggest factor affecting recovery on Katrina. You couldn't get gasoline within 200 miles of New Orleans because no electricity. No electricity, don't pump the gas. You can't pump the gas. The drainage network is going to be compromised in the reclaimed floodplains, places like the Boot Heel of Missouri. Railroad corridors are going to be disrupted, which affects getting heavy things in. Interstate and secondary highway network, airport runways and fuel handling facilities, and the municipal off-stream water storage tanks and the distribution system. Here's a good example of that. Here's the Louisiana offshore oil port loop system. We bring in about 26% of the nation's domestic production comes in through this area like this, and it comes up and distributes. Well, that line is coming straight through the New Madrid seismic zone right here. So that's going to affect the cost because of supply and demand for everybody. The cap line carries 1.1 million barrels a day of crude. The plantation pipelines, 26 million gallons a day, liquid fuels, and the Colonial Pipeline, 100 million gallons a day. So these are major infrastructure elements for the central U.S. In fact, those are the biggest ones. Other refined oil products, pipelines, you got all kinds of pipelines running this corridor. I call it the Tulsa-Chicago corridor. And this is right in the New Madrid zone here. We have 7 pipelines. I'm going to show you just on north side of St. Charles County right here going through. And you're going to have a shock factor because having fuel unavailable is going to cause a lot of turmoil. And that's going to be unprecedented. And it's likely going to necessitate rationing. That's never occurred before, by the way. We haven't had rationing since 1978. Crude oil and natural gas pipelines. Where do these things go? Well, we got 17 lines that actually cross the New Madrid zone. 17 major lines that cross the upper Mississippi embayment. And then we have the lines that come up and bunch and go through St. Charles County. Now, how did this happen? Well, this is all geology. Geology controls everything. You got all these lines coming across, and they want to come around this big metropolitan area. How do you get around a metropolitan area without going bankrupt and all the attorneys and everything? Well, what you do is you group everything up here into this agricultural area that's in the floodplain, and you go around St. Peter's and St. Charles and come out through the peninsula, and you cross over right here just above the confluence between the Missouri and the Mississippi. So you got 7 pipelines bunched right here just upstream of the water intake for city and county of St. Louis. About the worst possible place They have the water intake. So there's what it looks like on the geologic map. This is actually on the state engineering geologic map of St. Louis County and St. Louis metro area. There's the pipelines in red coming across. They used to be on the internet. They're not now. They come right down here and they cross right here, right above. There's the confluence right there. So they go through here. Now, is this a problem right here? No, that's buried right in here. That's the problem. We've had all kinds of breaks where these pipelines cross the levee right here. 17 breaks in this area since 1946. More than any other spot on the Mississippi River. Why? Because they're trenches. How do you backfill underneath a round pipe in a rectangular trench? You don't. You're supposed to put it in slurry of some sort. So they've got all these breaks that occur along here routinely. The problem is where these come back out of the floodplain over here and go onto the bedrock, that's where they'll break. That's where you'll have the problem. Because you have a sudden change in strain. So, how about cyber physical infrastructure? This is a big one. Why? Because we use cyber technology to exist each day. And so we have to look at our reserves and our redundancies in these kinds of systems, because they're going to topple and go down like a domino, just like the power system does, if we don't look at this kind of stuff with a very, very increasing view towards having a robust system. A robust system is one where you're able to break it in a few places, but the whole thing doesn't go down. And so we call this ICT, which means Information Communications Technology. We have to have just-in-time management procedures so that we handle this thing and manage it right at the time these things occur, because we depend upon these for all of our critical communications, like seeing if our kids are alive at the local school, or grandma's still alive at her place, or you're going to want to make those decisions before you get in the car and go running over there. Who do you go see first, kind of thing. Fiber optic cables, probably one of the greatest, I think the greatest inventions of the 20th century were fiber optic cables. Why do I say that? They're composed of strands of glass and plastic bundled together. They transfer laser light through those fibers through internal reflection, and they can transmit in tremendous amounts of data as compared to electrical conductors, such as copper wire. Now, here's what makes them so special. The next one. Third generation fiber optic cables. This came out in 1973. The third generation ones, which we have now, transmit 10 trillion bytes per second down a single strand using the same cables that were buried 25 years ago. There's no other technology that's out there that we've been able to retrofit like we have fiber optic. That's why everything's going fiber optic. Now, what does that mean? That means the reader we put on the end has gotten increasingly more sophisticated. We're using old fibers, but new readers. That's the only place you can do that. Wish you could do that with your car or with your body. This is the same amount of data in 1 second that's stored on 1,900 full-length audio CDs or 150 million simultaneous phone conversations. Wow. That's hard to even get a hold of. Now, here's your major fiber optic cable network in the St. Louis metro area. And this looks good until you get to the Mississippi River. So we see a lot of switching offices. These stars are switching offices. So we have a lot of redundancy in the network out in West County, but everything is grouping down and going across the Poplar Street Bridge, including all of the National Geospatial Intelligence Agency stuff from down here by the Bush Plant and Arnold, all goes up through that network across the Poplar Street Bridge. So the Poplar Street Bridge is your critical cog in the whole thing. And it's the approach spans on the east side of that bridge that I'm most concerned about, right here, going down. The main span's not going to go down. It's on bedrock. All right, how vulnerable is our electric power grid in the Midwest? This is what I get the most questions about from people who are on the more scientific and engineering side of thing. And they all ask me, is this our Achilles heel? Achilles heel, is that our weak point? Well, here's some of the popular concerns that I hear. And I've been on several call-in programs for some of the radio stations. And one of the concerns, number one, is there enough energy to meet the public demand? Yeah, there's sufficient energy in the national grid. If we look at Ameren UE, Union Electric System, they're based in these two states, in Missouri and Illinois. They supply the power for Rolla right down here. And the big factor here is stalling disaster recovery. Your recovery time today is the single greatest impact on economic loss. And the number one factor is electricity. Do we all use electricity? I mean, how are you going to charge the cell phone? Well, you can charge it with a car if you got a car charger, but you can't pump more gasoline into the car. Think about it. If you had an earthquake in January or February, that's when the big ones occurred last time, that's a lot more serious than having it in the summertime just because of the heating issue. All right. Where are most of the power plants? They're along the major rivers. In fact, my power, being I'm with rural electric out here, my power comes from this guy right here. This is the New Madrid plant, sitting right over Earthquake Central. What are the chances of it going down? About 100%. It's going to go down. So, are there sufficient spare parts on hand to repair the down power lines and transmission hardware? This is our Achilles heel. No. When did we start electrifying the United States? 1920s. St. Louis, one of the first cities to come up online. We had one there was one in city in 1913, Keokuk, Iowa. But basically, 1920s, and we got rural electrification out here in all parts of Phelps County about 1956. So 1920 to 1956. So that means a lot of the infrastructure is getting to be 80 years old. It's aging. Go out and look at a switching station here in Rolla. We have an earthquake. We have big, heavy components and transformers. Transformer falls down, or if we have a ceramic insulator here that breaks, where are we going to get a 25-year-old transformer or a 40, 50-year-old insulator? And the answer is, we don't have them. They wait till they break, and then they use what spare parts they have in the stockpiled in the yard in St. Louis, and then after that, they order them. They have to order them to be fabricated somewhere in Iowa or Nebraska or outer Slobovia. We don't know where. So that, we've never had a major regional disaster where we've had to order parts from a large area. Now, what about the power grid? Why aren't our public utilities upgrading their transmission networks to make them more resilient? And the answer is, nobody wants high-tension power lines in their backyard. They want them somewhere else. They don't want them in their backyard because of the cancer scares. And so the transmission network is congested, and that transmission congestion has been increasing every year. We especially see this with the brownouts in the summertime, and that's what causes the power lines to overload. And when they start overloading, we get these cascading failures. And what the utility guys are telling me is, this is the part we're having the biggest problem with. Because there'll be one critical component in the system that was just about ready to fail, that we didn't know about, and then it fails, and that wasn't in our model. And then that causes an overload over here, and that goes down, and then we get these cascading failures. So we've seen this with the windstorms and the ice storms over the past few years. So what happens then is we get transmission gridlock, and that's only going to get worse in the next decade because we're putting more and more juice through the existing lines that we have. And that's because of the worry about electromagnetic effects causing cancer, and the transmission lines are unsightly. Is a transmission network vulnerable to induce seismic hazards? Oh, yes. Any of the transmission towers that are on more than 15 meters of unconsolidated sediment, especially in the boot heel area, are very, very vulnerable. So how fast can you get it restored? That all gets down to manpower availability. What we have done a good job on over the past several decades is mobilizing more and more of the workforce to go into different states and help bring people back online. And we saw that during Katrina, after Katrina. What are the nagging uncertainties? All these things. The speed of recovery, the ease of recovery, duration, and the public perception are all very important. If a business has to shut down and move, it's very hard to woo them back. If they get operating in some other place, it costs them money to move every time. So we have situation reports today. This is one in Katrina. We have a lot more tools out there than we ever had before. One of the problems we have in the Midwest is that we do have 4 FEMA regions all meeting right here at the New Madrid seismic zone. So we're going to have 4 different regions having to coordinate with one another. And we have to have good disaster plans. And the way you get good disaster plans is you have to have exercises. You have to exercise your plan so that everybody knows what's expected of them when the disaster comes. And so that's what didn't happen with Hurricane Katrina with the school bus drivers. They had never exercised them to save money. So when the hurricane came, they just boogied. They took care of their families and left, and the buses got wet. So the biggest economic impact is how fast you can restore the power grid. We haven't done real good in that area on the windstorms and ice storms that we've had. They've been pretty local. We also have the underground storage tank issue, which we haven't had to deal with yet. That's been a big issue in all the earthquakes that I've gone and visited because it's the ready fuel. And we also have a barge traffic which has never been impacted previously, which we depend upon. So the actual cost is somewhere between $50 and $70 billion if we had a repeat of the New Madrid events, like a magnitude 7.7, a maximum event. It's very, very high. And you're going to have a fickle factor that's very hard to gauge, and that's the public confidence. Is the public confident that we're making a good recovery and that people aren't going to get up and move their businesses? So we're not able to gauge a lot of these kind of things in the current models that we have right now. And so they're working on those things, but that's going to take several decades to work out. So I'm going to go ahead and end it there because I need to this is our aging infrastructure. Just chart, I'll end it there. You see tracking different kinds of elements, looking at highways, sewer systems, water supply, electricity, telecommunications. And of course, as those systems get older, they get more vulnerable. Okay, I'm going to stop there and pass out the course evaluations. I need to get a volunteer who will take these back to Patty tomorrow. Somebody want to volunteer to do that? Okay. And I'll give you the envelope then. And all right.